Welcome to the talk, Lack of Quorum Sensing Leads to Failure of Consensus in Temnothorax and Emigration. My name is Jiajia. This is joint work with Lili Su and Nancy Lynch. Here's an overview of my talk. First, I'll review what an emigration is and the quorum sensing mechanism or step within the emigration. Then I'll introduce the motivation of our work to focus on quorum sensing and consensus. And then I'll introduce the semi-realistic models we'll be using. And then I'll introduce the consensus definition and criteria. Next, I will go into details about how we prove that after removing quorum sensing from the emigration process, with high probability, emigrations fail to reach consensus. Lastly, I'll talk about extensions and next steps. So first, a review of quorum sensing and emigration. This process is the process that an ant colony moves from one original home nest to another. And here is a full realistic model modeling the whole process through 4 phases, and this shows the process for an active ant. The colony is consisted of active, passive, and brood items, and only active ants are actively moving through this process to make a decision on which nest to move to. Here, this graph shows the most common pathways an active ant will go through, and quorum sensing is one step in this pathway. And specifically, when an ant senses that the number of adult ants in the current nest reaches a quorum size, she recruits through transports instead of tandem runs from the old home nest. This is picking someone up and moving her to somewhere, and this is leaving a nice trail so that she can follow, and if she doesn't like it, she can even go home. So as you can see, this is a much faster and more committed form of recruitment, and they're largely directed at passive and brood items. So this form of recruitment actually does the heavy lifting of moving the majority of the colony. And the motivation of this work, first I'll review some previous studies. So it's been established that quorum sensing enables transportation and accelerates the emigration, as I just talked about. And quorum size, the key parameter in this quorum sensing mechanism, is believed to tune decision speed and accuracy. Decision meaning deciding on which nest to move to. Speed is defined generally as the time when the original home nest is empty. And accuracy is defined as the percentage of passive or brood items in the best nest at the old nest empty time. So you can see here, accuracy measures the colony's ability to choose the best option among many. However, today we'll focus on this consensus metric, which is slightly different than the accuracy metric. So consensus measures the colony's ability to stay together as one contiguous unit, even if not at the best nest, but rather at a mediocre nest. That's acceptable too for consensus metric. So for our work's motivation, why might we want to connect quorum sensing to consensus? Because quorum sensing is a way to essentially lock in a nest choice once enough ants have chosen it. So it has a higher chance of accumulating population if the nest has reached quorum. However, we must be very careful because if the quorum size is too low, multiple nests can reach quorum and they all get locked in to accumulate ants faster, and that will result in a colony split. So we must be very careful, and these pros and cons prompts the question of whether quorum sensing is helpful for consensus at all. So this is our research question, whether quorum sensing benefits the colony consensus among multiple nests at all. And to answer this question, we come from 2 different perspectives. So on the one hand, we ask if quorum sensing is eliminated from this process, can consensus still be reached? And this is the focus of this talk, and just as a quick sneak peek, the answer is no. So this is the negative result part about after what happens after removing quorum sensing. So next, to fully answer this question, we also ask what is the effect if we add this quorum sensing back, and especially what about different quorum sizes? Are there quorum sizes that can help reaching consensus? And answering this question is a work in progress, which I won't be able to go into in detail, but I will touch on towards the end of the talk. So next, I'll talk about the models we'll be working with after removing quorum sensing. The timing model is discrete and round-based. In each round, each individual modeled as a state machine has a chance to perform a transition. And the environment contains a vector of nests, and nest NM has physical quality QM. One thing to note is that nest qualities are not known to ants before the emigration starts. Therefore, they're not an input, as in classical distributed algorithms. An ant only becomes aware of a nest and its quality upon discovering it for the first time. Therefore, the first discovery is generally quite important. And now I will detail out how we model individual active ants as coupled random processes. So I say only active ants here because, like I mentioned, passive and brute items cannot move by themselves, and without quorum sensing, the active ants will only lead other active ants on tandem runs, so the passive and brute items actually will not be moved as well. So they're not part of the analysis, and only active ants are our focus in this work. So in this work, we refer to each nest as a state. So being in a state is equivalent to being located at that nest. And as you can see here, first we model a two-nest environment where N0 is the original home nest that the ants will move out of. And N1 and N2 are the candidate nests, two of them in the environment, each having a different quality. In our work, nest N1 is of a higher quality than nest N2. And the way we model transitions out of the home nest, this is the home nest, and each active ant will start off being in N0. So there are two ways that an ant gets out of the home nest. One is through independent discovery, and one is through being recruited. The latter generally takes preference over the first one. So in order to reflect that, we define these two expressions as the event that an AI is recruited to N1 or N2 respectively during round T+1. So we use this expression as the probability of an ant being recruited to N1 or N2. So like I said, the total probability of an AI getting out of N0 during around T+1 is the probability of getting recruited. So this is showing going from N0 to N1 is the probability of being recruited to N1 plus alpha times the probability of not getting recruited at all to either N1 or N2. So this alpha here is the probability of independent discovery. And so there's also a chance that that N0 doesn't get recruited or doesn't discover other nests by herself, so then she just stays in N0. And then next, I want to introduce how we model the transitions from N1 or N2. So as you can see here, at either of these two states, there are two arrows coming out of them. So this U1 means N1, an ant at N1 chooses to stay at N1. So when an ant does that, she also attempts to recruit another active ant from N0. And the probability of doing this is proportional to the quality of this nest. So because N1 in our model has a higher quality than N2, U1 is higher than U2. So this shows the probability of this action, so then this action is just 1 minus this probability. So this makes sense because the better quality a nest has, the more likely that an ant will keep recruiting to it and keep staying or staying committed to this nest herself. Okay, and then next, we can talk about the execution model. We say that one execution is just one emigration. And in a round T, first, we allow ants in N1 or N2 to perform transitions in a random order. And then after that, we allow ants that are still in N0 to perform transitions again in a random order. So in this step, some ants in N0 will be forced to take the being recruited route to get out of the N0. So these are the ants that are not being recruited from it and are still staying in N0. So this is to enforce that recruitment takes higher priority. Then after that, all the ants enter the next round T+1 together with their updated states. One thing to note is that the whole colony state, which is the vector stacking all individual states, is Markovian. And now I want to introduce the delta consensus problem. So intuitively, if a large enough portion of active ants is in the same nest, from some point on, we conclude that, that a consensus has been reached. And specifically, how large a portion, we use 1 minus delta to represent that portion size, and delta is therefore a input to our problem, and it can be thought of as the proportion of ants exempted from the consensus requirement. And experimentally, it's observed to be quite small, like less than 10%, and it's also species dependent or sometimes even colony dependent. And then consensus probability C then is the probability of delta consensus for any emigration or execution. And we note that this definition is relevant to a lot of engineering systems because a lot of engineering systems also would benefit from having a small amount of tolerance to disagreements from some nodes. And now we're ready for our main theorem, which is an upper bound of the probability that the number of ants at Nm is higher than 1 minus delta n for m equals to 1 or 2. So as you can see, this is the criteria for consensus. And this upper bound here, as a side note, is different than an algorithm upper bound, and I apologize for the confusing terminology. But basically, we want to say that there's an upper limit on the consensus probability. And if we can show that this upper limit is small, then we can say that with very low probability, consensus could be reached without quorum sensing. And this is dangerous for survival. So here is the formal theorem statement, and you can see this expression is the limit, the upper limit or upper bound of consensus. It is quite small and decays to 0 exponentially fast as the colony size n grows. And I encourage you to read about it in the paper if you're interested in the details. And next, I will go into the actual proofs. So proposition 1, here's the structure of the proof. Proposition 1 comes from a key observation that any ant AI eventually leaves nest N0. And after that, her state transitions are independent of other ants' states and transitions. From proposition 1, we have kind of 3 branches of reasoning, which eventually will lead us to theorem 1. And now I will go through them one by one. This branch says with high probability, the number of ants staying at N0 beyond time t is upper bounded. And this is quite straightforward from the first part of proposition 1. Corollary 1 is very similar to proposition 2, but we find the time that at most epsilon n number of ants are still in nest N0. And then lemma 1, the second branch, says that each ant has the same limiting distribution pi star. And this again comes from the proposition 1 directly. And again, this is because after an AI leaves N0, she cannot be affected by other ants, and the only way she can be affected is through being recruited. And after she leaves N0, she cannot be recruited anymore. She can recruit others, however. And the third branch here says that as the passage of every round, AI has state distributions closer and closer to this limiting distribution pi star after she leaves N0. And this comes from the concept of Markov mixing time. And then corollary 2 is again similar to lemma 2, but we find the time that all ants are small delta close to this limiting distribution. And now, how do we put this all together? So, from the 3 branches, the summary is that after some finite time, with high probability, most of the ants or a lot of ants are out of N0. And for these ants, after some more finite time, each of them has state distributions close to pi star, which is the limiting distribution. And then with this understanding, we can apply Hofstad's inequality. This is after a finite time, ants not in N0 all transition independently. So applying this, we get that with high probability, the number of ants at NM is close to pi star NMN. So this is the limiting distribution times the population, active ant population. So if we compare this to the consensus requirement, we understand that it's very unlikely for the number of ants to reach this number if this is much higher than this. And that is the key of proving theorem 1 of how everything comes together. So most of the calculations here is to quantify how big this difference is and how likely it is to bridge that gap. And very briefly, this same analysis could be extended to environments with more than 2 nests. And please go read about it in the paper. It's very straightforward. This is an example of adding another nest. And here is again the theorem statement. As you can see, similar arguments still hold conclusions. And then next steps, the work in progress. What if we add back quorum sensing? This is the second part of answering our original question. So we have a model that we analyze, and we model quorum sensing as a total commitment. Once an ant sees quorum at one of these 2 nests, she just commits and she just keeps transporting a passive or brute item to the nest. So now there are 2 forms of recruitment. One is some ants are doing transport, some ants are still doing tandem runs. And the whole colony state, however, is still Markov. So here are our preliminary results. We show quorum sizes that are expected to be sufficient for consensus when delta is equal to 0. And here is a 3D representation where this axis is U2. Is U1, and this is U2, and this is the desirable quorum sizes. And as you can see, the lowest value here goes to about 30%. And second result is we show the quorum sizes that are expected to be necessary for consensus when delta is 0. The above are all for an average emigration, and in the next manuscript, we'll formally define what an average emigration is. And these quorum sizes are, of course, parameterized by model parameters. To sum up, our results suggest that quorum sensing plays an important role in avoiding splits and reaching consensus. And one important future direction is to make the model more realistic, for example, adding back the surge state, which you can read about in our previous paper, or incorporate actions that take multiple rounds or other timing aspects. Another thing is to analyze other mechanisms using similar methods. Since we provided an example that rigorously analyzes the key mechanism that influences the outcome of the emigration, we hope you continue this work using similar methods.